Okay, this third video segment will be general comments about the issue of beam, symmetry of beam, and the orientation. First of all, I will do this problem in Catia in a few minutes, but I would like to refer to a concept of a simply supported beam. In real life, or in an experiment, if you want to create a simply supported beam, probably this is the way you set it up. So two rollers, a plate on it, or a beam on it, and then load it. When it comes to analytical solution, then at least in the strength of material course, the stress analysis course, when we talked about simply supported beam, we probably drew for you something as in the top left corner. We could have drawn the one in the middle or the one at the bottom. In principle, there is a fundamental difference between these three. For example, the bottom one is unstable. The slightest disturbing force in the horizontal direction make it move. The one in the middle, it's got axial load developed in it because the two ends are fixed. Whereas the one at the top, because of the roller support on the left, there is no axial force. However, for the linear elastic analysis, that is the primary goal of this course, focus of this course, we treat all of these to be the same. Okay? Now, how do we model this thing if it is to be done in finite elements? So what we're going to do is, for example, if you look at the one on the top right corner, this is what I'm going to do. I'm going to create a model which is half the length of the beam. This end is pinned. Okay, in other words, it is free to rotate about the x-axis, but it cannot translate in y and z. Obviously, it will not rotate about the y and z axis. Now, as far as this end is concerned, you can view this as being on a roller like this. See? On a roller like that. And of course, you have to put half the force here, F over 2. So the point is that, my point is that you cannot just draw half of the length of the beam and then put the force here, or F over 2, and then maybe you fix this point, because this is going to be unstable. It can actually move as a rigid body. So you have to apply some kind of a restraint to the place where artificial surfaces, or in this case, points being created. In solid model, what we did, if an artificial surface was created, or plane of symmetry was created, we use surface slider to mimic the restraint there. But for beams, what this is saying is that there is no displacement in the y direction. There is no displacement in the y direction. However, it can move up and down, as you can see. There is a very clear rule that I'm going to specify later on when I do the problem in the beam. Okay, so for now, at least you got the basic idea of how we're going to model this problem. Okay, let me see now. Let's go to Catia, start a file, a part file. Okay, let's go to part design and basically draw half of the length of the beam. Now, if the beam is 20 inches, I'm going to assume that the entire length of the beam is 20 inches. Therefore, I will take only 10 inches of it. So on a convenient plane, say on this vertical plane, I will sketch, I'll sketch a line that is 10 inches long. This is going to be half the length of the beam. All right. Well, actually, let me draw it so that this is starting at the origin. That's not necessary, but I have a reason for wanting to do that. Okay. Coincident. Right there. Okay, let's try it one more time. This and that coincident. I just want to make my job easier, that's all. You don't have to do this. Alright, so this is going to be 10 inches long. 10 inches long. Half the length of the beam. Alright, exit. Remember, you have to join this. So you go to wireframe and surface design. Join it. Where's the joint? Right there. That's sketch. Okay, it's joint. Apply material on it. Metal, steel on that part. Alright, now for a reason that may not be obvious to you, what I'm going to create is 2 points. Well, actually, let me make it 3 points. 1 point here. So let's see now, 3 points with these coordinates. For example, let's make x equal to, I don't know, 2 inches. So it's right there, you can see that. One is 2 inches up. So 0, 2 inches up. And one kind of an intermediate one. How about 2 and 2? 2 inches and 2 inches. 2 inches in the x direction and 2 inches up. It may not be obvious why I'm doing this thing, but you will see that when it comes to defining the orientation of the beam, I'm assuming that the cross section of the beam is a rectangle with, let's say, dimensions, I don't know, maybe 10 millimeters by 20 millimeters, something like that, or maybe 10 by 30, 10 millimeter by 30 millimeter. And then I'm going to need these points. You can see that. All right, so let's see. We go to analysis and simulation, generative structure analysis. We are doing a static analysis. First, you're going to mesh this beam right there. Okay, good. Now, we're going to define the cross-sectional property right there. Cross-sectional property. We don't want cylindrical, we want a rectangular. And the size, you click on the wrench, let's say 10 millimeter in Y. Be careful now, the Y and Z that this is referring to may not be the Y and Z that is in the global direction, and in fact it is not. So what I'm saying is that 10 millimeters by 30 millimeters. I'm putting big numbers here to emphasize the visual effect when we see it. Okay, good. Now notice that I cannot close this dialog box. In the case of circle and tube, I could close it, but not anymore, because this orientation geometry becomes important. But first of all, the support is here, right there. There's a support. So, for orientation geometry, let me select this point. Notice that, look at the way the beam is oriented now. Right there. Let me change, instead of that point, this point. See, it turns it around. Or let me select this point. It puts it at an arbitrary kind of orientation. So when it's a non-circular, non-tubular beam that we're talking about, this orientation point is important. Now I don't want it this, so let me use that guy or this one. Doesn't matter. All right, and then we can close it. So you understand what the role of orientation point is? Okay, good, good. Now we're going to go and apply the restraint. So this end, if you look at the problem that I had, was pinned. Okay, so we're going to click on the user-defined restraint. Let me uncheck all of these. So that point is pinned. That means if you look at your coordinate system down here or the compass, it does not move in the direction X, Y, Z, and it does not rotate about directions Z and Y. Directions Z and Y, which are directions 2 and 3. It can rotate about X, and that's precisely what we mean by simple support. Now we go to the other end. this end. This end, let me uncheck all of these. This end was in a plane of symmetry. And the plane of symmetry for this end was parallel to the zx plane. Just look at your coordinate system here, zx plane. So if the point lies in the zx plane, it does not move in the direction 2, direction y. Now, free in direction 1, cannot move in direction 2, cannot move in direction 2, and cannot move in, and free in direction 3. The rule for these rotations are exactly the opposite. So if something is checked here, must be left blank. If something is not checked up there for translation, it must be checked. Now you may get lucky and you either don't do this or don't pay attention to it, and just because of sheer luck, it may work, but that does not make it right, and points will be deducted. All right, now what about the load? The load is at this end, so you apply a force at that point. Let's say we applied, the original load applied was, let's hypothetically say it was 1,000 pounds, okay? 1,000 pounds, but because you're using symmetry, half of that is being applied to the piece that we're modeling. So in the direction Z, negative 500 pounds, 500 lbf. And we say okay, and you can see that it is right there. There is a force. Okay, and we can save it and then run it. I'm not going to save it because it's a straightforward problem, so I'm just going to run it. It's all done. So look at the vertical deflection. Let's put it in a view that we can recognize. So the front view. Yeah, good. And let's animate this. This end is pinned. This end is pinned, and this is moving up and down. If you want to see the deflections, you just click on the displacement. It shows it to you in the form of vertical downward arrows with different components. Now these are millimeters, by the way. And remember, I have a problem with my graphics card, so if I plotted it in the way the contours look, this is wrong. Okay, that's sheer wrong. Okay, so let's put it back to symbols. All right, folks. So that takes care of this issue. We discussed symmetry boundary conditions, half the load, and yeah, there will be more problems about the symmetry issue discussed in the lab and in course in future